before we begin class. So along with that little bit of a schedule, that today we'll work on conservation of energy is the main focus. Wednesday, your Rube Goldberg projects are due. That will count as a big test grade. So it will be a grade.
Mine's good.
Hunter, or Zion, I did get your video, but I gave those comments, excuse me, that it need to be a little bit more longer in the sense that you need to convert energy. And you'll see that today. I'll talk to you about how you're converting kinetic to potential and potential to kinetic.
Oh, Miss Rodriguez, that was at my mom's house. I'm at my dad's house. I don't got anything over here.
Okay, well, we'll figure something out. I mean, that's why I have different letter grades to give, right? So just because you do it doesn't mean you're going to get an A.
True.
And to get your full credit, these are the expectations. So you did well. It's not
As
a
long
bad
as it's a
grade.
passing grade.
It should be passing. You did all right.
All right.
Okay. Okay. So that will be due on Wednesday. I'll clarify some of those things with energy today. Monday quiz, Wednesday wrapping up. Okay, that's our schedule for the next 4 classes. That's it. Henry, you excited? It'll be nice. It'll be really nice to start summer vacation before Memorial Day, or Memorial Day weekend begins summer vacation. I like that schedule. All right, so then moving forward, today, on your Rube Goldberg, what we will be looking for is you have to have 3 energy conversions, and you're going to show it to me live. If it's hard for you to show it to me live and you want to take a video with your camera on your cell phone and email that to me, I will accept that, but I'll show that to the class on Wednesday. However, it can't be so long. So I think in email, those videos have to be pretty short. My preference is that it is live. So if you can do it live, I might even give extra credit for that as opposed to video, because that was the intention. But they will have to be quick because we only have so much time. So with that said, the other thing we did live last week was the juggling contest. And you all did great. You got credit if you participated, but my F period dominated. I would say more than half of those kids did 3 balls. And Eric Logston did the best. So he was like 22 seconds with 3 balls, having never done it before. So it was a pretty good. So you have to congratulate him. He was the best juggler of everybody. For somebody who didn't know, Chase Bruce is the best juggler, but he already knew how to juggle. So I can't count that as much improvement. But he did well. All right, so let's begin class. Does anybody have any questions before we begin regarding homework, projects? Everybody's all good? Okay, Henry, can you lead our prayer today?
In the name of the Father, Son, Holy Spirit, amen. Our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done on earth as it is in heaven. Give us this day our daily bread, and forgive us our trespasses, as we forgive those who trespass against us. And lead us not into temptation, but deliver us from evil. Amen. Father, Son.
Thank you. Very good. Henry, if you don't mind me asking, how's your dad doing?
He's all right.
He's not back in the hospital, is he?
He went in a couple times.
Through this whole thing?
Yeah, he's been in 2 times.
Wow.
But he's getting better, I think.
Okay. He's home
Feel
now?
better.
Yes, sir. I mean, yes, ma'am. He's home.
Good. All right. It's been in my prayers. That's a tough time to not feeling well with the hospitals the way they are.
Thank you.
Mainly because they limit everybody coming to visit them, right?
Yeah, no one could go see him. My mom or like nobody.
That's awful. So it makes it hard on him for recovery, because I think there's something to be said about those personal relationships and how it energizes you and motivates you. So.
Yes.
All right, gentlemen. So today, May 11th, as we end our year, getting close to the end, I thought this one was definitely appropriate for my senior class today, which was their last class today. So here is our mustard seed of today. A very dear friend of mine finished one of her letters with this line: "Help me to remember that when I have God, things will always be in place. I pray we help each other to remember this. So I told my seniors, one thing that's really neat about Benedictine is this brotherhood that you all form around faith, and that with God, anything is possible. So not only are you guys making great friends with one another, but you're making friends in faith, which you need to hold each other accountable to, when things are rough, to not forget to pray and that God is around. So I know myself, I as I'm old and now, the best friends I have are those that have come from my church, that have consistently held me accountable to praying through things and finding peace in God's plan. So with that said, that is how I read the mustard seed for today. So I hope you guys are doing well, and we will continue. So the first thing we have to do is, we never did go over your worksheet that was due last class on potential energy and kinetic energy. So I'm going to pull it up, and I'll give you a minute to find yours. So it was not due today, it was actually due last class. And let's see if I can, should be here. Well, maybe I closed it out. So I'm going to have to open it up again myself before I share. Okay. Sorry about this. Thought I had it up. It's one nice thing about potential and kinetic conceptual questions. I think this is what I want. Computers, I can have multiple windows open. It really does help. All right. So now this is the document that you are looking for. Looks like this. So at the top it says conceptual questions, energy, define potential and kinetic. These are the kinds of questions you're going to see on your quiz next week. Okay. For the sake of time, I'm going to answer most of these, but occasionally I'll just call on you. So if you guys can all be ready to quickly answer what you may have written in here, I'm going to bounce between typing on it and writing on it, depending on what the question is asking. Okay. So quick review. Does anybody need more time to find their sheet? You guys did great on getting that homework done. I just want to make sure you have the right answers. Everybody's got it? Okay, so let's go over these questions. If you don't have it written similar to me, it doesn't have to be exactly the same. By all means, copy down the right answer. Okay, I do not post these solutions, so that's your motivation for being here in class. All right, potential energy. Nathan, you want to take this one? What is potential energy? What is kinetic?
Kinetic energy is the energy an object in motion possesses.
Okay.
And then potential is the energy an object possesses within itself relative to other objects.
Okay, the energy of motion, potential, the energy due to position. Good. And again, you don't have to use those exact words, but you need to know that an object that is moving, whether it is spinning, rotating, moving in any way, then we would say it has kinetic energy. So an object that has potential energy is the result of where it is positioned. So that's basically for gravitational potential and electrical potential energy would make a difference on its position. All right. So let's see. TJ, you're with us. Is energy a vector or a scalar quantity?
Is it a scalar?
Scalar, and what does that mean to be a scalar quantity? A vector has magnitude and direction, but a scalar has... TJ?
I thought a scalar had magnitude. Wait, scalar has only magnitude, right?
Only magnitude.
All right.
So magnitude only, right? Whereas a vector quantity has direction to go with it, magnitude and direction. Good. All right, what are the equations to calculate gravitational potential energy and kinetic energy? So I will go ahead and do this one. because I can write in here now. So our potential energy, gravitational, is mgh. Now, some of you from your textbook, you may have written it as mg delta h. And the delta, remember, means change in. So back up to here where you say with respect to other objects, the delta means where are you putting your zero position. So I'm okay with you leaving out that delta. That is fine. So next, what is kinetic energy? So kinetic energy equals 1/2 mv squared. And again, you might have seen that as delta V. So it's your final velocity minus your initial velocity. Okay. Good with those? Okay, just because I'm going to scroll up here, I'm going to clear out those drawings. And slide our file up here. There we go. So number 4, car lifted, and then number 5, the 2 cars are raised. Okay, so in number 4, the car is a certain distance in a surface station is lifted and therefore has potential energy relative to the floor. So you can imagine here is the floor, and you'd have like the car lift up here, right? Where we would put our car on top of that lift, okay? So if it was here at that particular height, and then instead we raise it to twice the height, and now your car is way up over here. So if this was your original H, and this now becomes 2H, okay, how much more potential energy would it have? As we just wrote that equation, potential energy is mg delta H. Well, that delta 8 would be now 2H. So that's the effect of having twice your potential energy. So with the 2 being on the right-hand side, you'd end up with twice the amount of potential energy as you did over here. So if this one is simply potential energy equals mgh, then that's just going to be mgh. So of course, mg2h is twice your potential energy. In number 5, 2 cars are raised to the same elevation in the service lift. If one car has twice the mass as the other, compare their gains of potential energy. So now if they're lifted to the same height, so we have this car, right? And it's lifted to a height h, but then I have another car that's twice as big, so much bigger, but lifted to the same height. This one has twice the mass, that one has single mass. So the potential energy of this one over here would be mgh, and the potential over here would be 2mgh. So it'll have twice the potential energy. So mass and height are directly related with your potential energy. So if I double my mass, I double my potential energy. If I double my height, I double my potential energy. Okay, can I have a quick thumbs up? The Zoom thumbs up, everybody following? Ethan, good, thank you. Kendall, all good? All right. I think he's with us, right? I lost my Kendall there. Okay, so let's go back, continuing on here. Now, if we go back to...
Ms. Rosriver?
Yes, Jacob?
Go to the bathroom.
Sure. You might, if you can wait till we're done with this, that might be a better choice, but if you need to go. Okay, so now if we're talking about kinetic energy down here, so if your kinetic energy is equal to 1/2 m, not sure why this is not writing very well, m v squared, and I double my velocity, so then my kinetic energy becomes 1/2 m times twice my velocity squared. So if my velocity is twice as much, that 2 also gets squared. So it's really 1/2 mv squared times 4. So the 4 comes from the 2 getting squared. So this is my equation for my original kinetic energy. So doubling my velocity gives me 4 times the amount of kinetic energy. So that's the answer to number 6. Doubling your velocity is 4 times. Whereas when it came to numbers 4 and 5, potential energy, doubling the height, doubled the potential, doubling the mass, doubled the potential. But for kinetic energy, doubling your velocity does not double your energy, but rather quadruples your energy. But if I double the mass, so let me clear that out. In number 7, if we double the mass of the car, right, now your kinetic energy, which is equal to 1/2 mv squared. If now I have twice as much mass, we would have 1/2 2m times v squared. Well, in this case, that 2 does not get doubled or does not get squared. So it'll just factor out, and I'd have 2 times my original 1/2 mv squared. So doubling my velocity doubles LES, the kinetic energy. Whereas up here, doubling my velocity quadruples would be your answer. I'm sorry, my pen's not writing so well. Give you a moment just to make sure you got all that. Okay.
Wait, Miss Risenweaver, what are we doing again?
We're going over your homework that was due last week, but we never went over it because we did the juggling.
Oh, dang. I
Okay.
suck at juggling. That joint was hard.
Okay, and number 8 is the same question as number 3, so I'm not going to repeat that. We're going to skip down to number 9, asking similar questions. When the velocity of an object is doubled, by what factor is momentum changed? By what factor is kinetic energy changed? So let's take a look at these two. So remember on this one, momentum and energy are characteristics of an object, right? So if we talk about an object's momentum, it has it as a result of having a mass and a velocity, whereas the object's kinetic energy is also the result of it moving. So an object moving has kinetic energy and momentum. If I double my velocity over here, if I get 2 times 2v, that's the same as 2 times my original mv. I can factor in my 2. So my momentum would be just twice as much, right? So I would end up with twice as much momentum. So the answer to that is you double momentum. But as we saw earlier, if I double my velocity over here for kinetic energy, m times 2v, since that gets squared, my 2 also gets squared, so I'd have 4 times the original 1/2 mv squared. So the answer to what happened, by what factor does kinetic energy change? That answer, it is 4 times as much or quadrupled. Okay. Reed, good on that one? Joseph, Nolan? All good, all good. Nolan, you with us? Oh, is that a thumbs down or your phone upside down? Are you good to go? There we go. Okay. All right, number 10, which if either has greater momentum, a 1 kilogram ball moving with 2 meters per second or a 2 kilogram ball moving 1 meter per second, which has greater kinetic energy? All right, so again, looking at a momentum equation, that's mv. So the first one, we have 1 kilogram. Okay, so let me see if I can do this a little different here. So in our first one, we have 1 kilogram, right, times 2 meters per second gives us a momentum of 2 kilogram meter per second. For the next one, where I have a mass of 2 kilograms, but a velocity of 1 meter per second, my momentum is still going to be 2 kilogram meters per second. So this should be momentum, momentum. So considering magnitude only, they both have the same momentum. So I doubled the mass, but half the velocity, I get the same momentum. However, with kinetic energy equaling 1/2 mv squared, the kinetic energy of the 1 kilogram mass, its velocity of 2 meters per second squared. 2 squared is 4 times 1 is 4 divided in half, gives us 2 joules. So the kinetic energy of that would be 2 joules. However, if I half the mass, or double the mass, but half the velocity, because it's 1/2 mv squared, you'd get 1/2 2 kilograms times 1 squared. The 1 squared is just 1, times 2 is 2. Taking half of that, you end up with 1 joule. So this one has the greater kinetic energy, the one that has the smaller mass but goes faster. When it comes to energy, velocity causes a greater change in kinetic energy than it does for momentum. Okay, so you have a greater change in kinetic energy than you do in momentum for a change in velocity. Okay, and then finally that leads us to number 11. So again, I'm just going to pause for a moment, give you a chance to write that down if needed. And let's move on to number 11. Okay, so for number 11, scroll down here a little bit more. If two objects have equal kinetic energies, do they necessarily have the same momentum? Nick, what do you think about that one and why? So if two objects have the same kinetic energies, do they have the same momentum?
No,
Correct. So
not
no, and why not though?
because it depends on the mass of the objects.
Okay, but more importantly, what did we see up here in this one? What matters more when you're comparing kinetic energy and momentum?
I can't hear you. Hold on. And my mom is.
Kinetic energy depends on V squared, whereas momentum is just V. Okay, so kinetic energy depends on V squared, momentum depends on just V. So just because they might have the same momentum doesn't mean that they also have the same kinetic energy, because that matters on how do their velocities differ. Okay, so that's going to make a difference on how do their velocities differ. Okay, so any questions on that worksheet? All good? Okay. All right. Everybody has some paper and pencils. Hopefully you're writing that down. Let's talk about conservation of energy. So I'm going to go through this really quick and then come back and use our simulations from the PhET simulations that you guys use for one of your labs. So let me get my screen set up so you can clearly see my whiteboard as we are working here. And get rid of this picture from last class. Okay, so what do we know about energy? We have two types, right? Kinetic and potential. And just like with momentum, we found that an object's momentum is constant. okay, unless there is an outside unbalanced force, right? So if we have an outside force, then we could change an object's momentum. Same thing with energy. If we have an outside force, we're going to change an object's energy. That energy change will do work on the object. And we haven't talked about work yet, but as you read in your textbook, work is a force applied to an object that changes its energy. All right. So we're going to first begin with, if I have no outside forces, that includes friction, somebody pushing on it or anything, then what we find is the energy of the system is constant. This is called the law of the conservation of energy. Okay, law of the conservation of energy. Energy cannot be created or destroyed. So in the absence of an outside force, the energy of a system is constant. Okay. In the absence of an outside force, the energy of a system is constant. So mathematically, what we would say is that the total energy when you are in one position, so I'm going to say total energy subscript of 1 must equal our total energy at 2. So from position 1 to position 2. The only energies we have is kinetic and potential. So just like when we say total, it's the sum of all of your energies added up at one position must equal all your energies at another position. So the only energies we can have is potential and kinetic. So for my total energy, I would say my potential energy at position 1, that's the subscript of 1, plus my kinetic energy at position 1 must equal my potential energy at position 2 plus my kinetic energy at position 2. So potential energy at 1 plus kinetic equals potential energy at 2 plus kinetic energy at 2. We would substitute our equations for potential. So remember, potential is mgh, kinetic is 1/2 mv squared. The classic question for this would be if you'd have a ramp, something like that, okay? And on that ramp, you put a ball of some sort, and the question would be, how fast is the ball going at the bottom of that ramp? Or something else, a skateboarder, we'll see on our simulation, it's a skateboarder. Let's say this has a mass equal to 2 kilograms. Here is our table that we have that ramp on. And this is a height. We built the ramp to be up a height of 1 meter. So we would choose this as our potential energy to be 0 position. So remember, the height is relative to something else. So that was our very first question that Nathan answered very well, to say potential energy is relative to something else. So my height I am measuring here has to be relative to something else. Okay. So reminder that you can close off all those videos off to the right. So if my writing is getting covered by faces, you may close all that by hitting in the top picture the single bar, and then that can be moved around to different places. Right. Okay, so 1 meter, mass of 2 kilograms. How fast would it be going down here if there is no friction, right? How fast is the ball going at the end of the ramp? Okay, so in all of our situations of motion, we can use force calculations, we can use our velocity equations, motion equations, we can use momentum, and now we're learning another method in energy. This is a very simple setup, but overall, it's the premise behind all of this. So what we're saying here is if this is position 1, the energy that I have here must equal my total energy here because I did not have any outside forces adding energy or taking energy away. Okay. So the way I would want to write this is to say, first thing, we list what we know, right? What we know is the mass equals 2 kilograms. We're going to call this position 1. At the top of the ramp, you need to designate where are your positions 1 and 2. So that's going to be position 1 and position 2. So my height 1 is equal to 1 meter. My height at position 2 is 0 meters. I have no height, which means if I have no height, I have no potential energy at position 2. My velocity at position 1 is 0. It starts from rest. I just dropped it. Okay. And I'm looking for what is my velocity at 2. So again, you draw your picture, evaluate your situation. What do you know? What do you want to know? So if there are no outside forces, I can solve this problem by using conservation of energy to say the energy at 1 must equal the energy at 2. So I'm going to come over here and use that. But usually the equation becomes very simple. Potential energy at 1 plus kinetic energy at 1 equals potential energy at 2 plus kinetic energy at 2. All of that energy must be the same everywhere. Since I am not moving at position 1, Joseph Kelly, what is true about my kinetic energy at position 1? So Joseph Kelly, you might be muted if you're still with us. What is my kinetic energy at position 1?
You don't have any kinetic energy at position 1.
That's correct. Why not?
Because it's not moving. It has more potential energy because it's higher off the ground. It's not moving.
Very good. So we have no energy, no kinetic energy here. It's all potential. So in this case, we would make this equation easy before I go to try to solve it. And I would say all my kinetic energy is 0. When I come down, I got to choose that I'm using this to measure my height. I already designated my potential energy here to be 0 because there is no height. So in my equation, this becomes 0. So what's happening in this situation is that all of the potential energy at position 1 becomes all your kinetic energy at position 2. So all your potential must become all your kinetic. My potential at position 1 equation would be mgh at position 1 equals 1/2 mv at position 2 squared. So I'm simply substituting in my equations that we just wrote about on homework. What is potential energy? What is kinetic energy? Plug those in, and remember, step 4 is to rearrange your equation to get your unknown by itself. Right? So, miles, what can I do to get the V by itself? The V2. How would I get rid of 1/2 m?
You can divide it.
By both of that? So divide both sides by 1/2 m. Okay, if I divide both sides by 1/2 m, that cancels over here. Over here, does anything cancel? Miles, I'll stick with you.
No.
Nothing cancels. Do I have anything up at the top that's at the bottom?
The M.
So would the M cancel?
Yes.
Yes. Okay, everybody think about that. That M just canceled, which means it doesn't matter if I roll a bowling ball or a marble down here, both will have the same speed. They will not have the same energy or momentum because both of those quantities also depend on mass. But no matter what I drop from the top of this, as long as it goes through that height, they will both end up with the same speed. Rearranging this equation, if I divide by 1/2, that's the same as multiplying both sides by 2, right? So my equation becomes 2GH at position 1 equals V2 squared. So we plug in our numbers, 2 times 9.8 meters per second times the height of 1 meter equals V2 squared. So 1 meter, 2 times 9.8 gives us 19.6, but the units are, and this is meters per second squared, meters squared per second squared equals V at position 2 squared. So if that gets squared, how do I get rid of a square? Nolan, do you remember? How do we get rid of a square?
No.
All right, let's think about it. What's the opposite of squaring something?
Square rooting? No.
Square rooting it.
Square rooting.
So we want to square root both sides next, so that I end up, the square on the V cancels. The square root of 19.6 is what is our velocity. So I have to square root that and I get 4.43. So 4.43, your units also get square rooted, meters per second equals my speed at position 2, no matter what I roll down this ramp. So it doesn't matter what I put down there, my speed is still going to end up being the same. Okay, so the idea is whatever energy I have here ends up over here. If I have all potential here, that becomes all kinetic right here, right? Ethan, what is going to happen at a position right here? How would you describe my motion or my energy right here?
Half
Half of what?
velocity, or half the height.
It might not be half the velocity. We'd have to go back and calculate, but that's half the height. If it's half the height, then I have half my potential energy and half kinetic energy, right? Up here, I have all potential energy. Down here, I have all kinetic energy. So halfway between, I'm still moving, so I have kinetic. But because kinetic energy depends on V squared, I would not have half the speed. That's going to depend on the square root of that. But all the way along from here to here, I have both kinetic and potential. Up here, I have more potential than kinetic, half more kinetic than potential, all kinetic. So slowly, my potential energy is given up to become kinetic energy. And this is what I'm talking about in your Rube Goldberg. I want conversions from kinetic to potential, potential to kinetic. So this is the easiest, and then you hit something. Well, when I hit something and it might be moving and fall off into something else, then with respect to the floor, this object takes its potential and changes it to kinetic, but it already had kinetic there because it got kinetic from this one's potential. That's what you're going to have to explain to me next class. And your textbook, this is all chapter 7 in your textbook, so that'll help also in terms of looking at energies. All right, now
This right here, I can't see. Can I finish writing?
oh, yep, sorry. Try
Can
to
you
make
put the
it
camera
quick.
down a little bit?
There you go. You know how to do a screenshot?
Yeah, I screenshot it. Thank you.
You good now?
Yes, ma'am.
Okay. If that helps, I personally would want it written in my notes. All right, so before I continue, everybody following along okay? Okay, so let's go back to this view. Hmm. All right. All right, so I moved that up in there. There we go. Go back to my gallery view. That's what we want. All right, so what I would like to do now is I'm going to screen share a simulation on the computer with you to talk about what we just saw. So Joseph Kelly, you still there? Jacob, whenever I do my screen, people would like to check out. Miles, you're still here. All right, Jacob, I see ya. Luke, you with us? So give you your, no voice today, Luke? All right, I'm going to do a little screen share here with you to show you this simulation of what we were just talking about. Kind of cool. Let's see. Need to go to the internet. So that was our homework, right? All right, so exactly the same ramp that we were just talking about, right? So here's our ramp that we're talking about. Here I put the grid in. So at most, the skater is going to start up here. And you can see the red dot underneath the skateboard. I'm going to try to set that red dot exactly at the height we were at right here, which is 6 meters above the ground. All right. So as the skater goes down, right? And as they go, as we were just talking, I'm going to pause it right there. When they reach the height of 2 meters, they have both kinetic and potential energy because they are a height above the ground and they are moving. When I continue through and I get to the very, very bottom, that's going to be where I have my maximum speed because I've given up all of my potential energy to change it into kinetic energy. Okay, and this is nicely shown if I put up a pie chart here and I eliminate that there is no friction. You can see the red that's in the pie chart. That's due to friction. So if I have no friction, watch what happens when I start. So the blue is all your potential energy, right? So right now I have all potential energy. And as I go through, that potential energy is now changing to kinetic. Again, I'm going to get rid of all of our thermal energy, which would happen because of friction. So all my potential is now changing to kinetic as I keep on going, right? Oh, I got to change my friction. Let me get rid of friction here. Now my kinetic becomes greater than my potential, but I have both at that position. It's not until I get towards the end that now I become all kinetic compared to my potential I had at the beginning, right? But what would happen if instead I build a different ramp and I want to make them, well, I guess what I want to show you is no matter this ramp, if I change my mass to being a very, very big skater, so notice my skater, but I put my speed up on here, by the time I get to the end, okay, so here's my skater, same thing, no matter my mass, potential changes to kinetic. When I get to the end, there's my speed, right? So if I go back to my skater and I go back to a small mass and we make our skater very small, watch what happens to the speed. Whoops, whoops, whoops. Oh my goodness, that skater's going to die. Fell all the way off. All right, so watch my speed. As they get to the bottom, if you remember the big skater, hit the same speed. So in the case of conservation of energy, what we saw mathematically is mass does not matter in this situation. So my question next is, I'm not going to send them yet, does it matter the shape of my ramp with that speed? Okay, so that's a very important question. Now I change the shape of my ramp Here comes my skater. Notice the pie chart up above their head. I'm still changing potential to kinetic, but notice how much more potential they have at this middle point compared to kinetic. So the difference here is they're going to go really slow for a long time because I'm not changing my height of my ramp a lot at the beginning. And then at the end, all of a sudden my potential becomes a whole lot of kinetic, still reaching the same speed by the time I get to the bottom. So it doesn't matter what my ramp looks like. If I have a ramp like this, I will change my potential to kinetic much quicker than when I'm like this. My potential barely changes until I drop steeply, right? So what would happen? Many of you like to ride roller coasters, right? So if we restart our skater and I redesign this, let's put them all the way back up here, right? So let's redesign our ramp to go back up. How high can this skater go back up? So I'm going to lift this ramp higher than what we had here, right? And I'm going to let them go. So what is the maximum height they can go here? Okay, so is Josh Hughes with us today? All right, no Josh. He check out. All right, Reed Miller. Where are they going to be able to stop? What's the highest the skater's going to go again?
Like right, like above where the number 2 is.
Okay, so just barely above where number 2 is?
Actually, probably
What do
higher
we know
than that.
about energy?
Yeah.
So what has to be true is energy stays constant, right? So when I get here, I'm going to have the most kinetic energy because that's the lowest I can go, where I give up all my potential to that kinetic. What happens as I start to head back up here?
You slow down.
I slow down because now that potential, that kinetic that I had down here, starts to turn back into potential. But energy must be conserved. So the highest that I can go is to head and get back to the same exact height that I was, right? If I go higher, that means somehow I got more energy involved. So let's see if that's the case. So if the skater goes back and we don't lose any energy to friction, see if I can switch it back to. Now we go back up and we go back to potential, right? Goes back to the same height to which they were, and they're going to go back and forth. All right, let me pause that. Go to normal speed so it goes a little faster. Okay, so as they slide down, kinetic and potential constantly change. And I can't go, even though my ramp is higher, I can't go higher than what I originally was, right? All right, we are out of time, gentlemen. So when you are dealing with making your Rube Goldberg, that's the key. I want you to try to be thinking of conservation of energy. See if you can get a marble to go up over the ramp and just barely stop, and then it comes back down and it seems like it gains energy, but it really doesn't. It just changed that kinetic energy back to potential. All right, so homework tonight is to answer some questions about potential energy and kinetic energy conversions in conservation of energy, and then Rube Goldberg live for next class. Chris, can you do that? Oh, he already checked off. Nope, there he is. All right. You going to get your homework done on time? Okay. Joelle, you good to go? All right, boys, have a good evening. That does it for physics today.